Welcome back. We are in session 6. We are talking about data preparation, data pre-processing. In the pipeline of data science project, remember you have a raw data. You make the data ready, pre-processing, preparing the data. Then when you have the data in a structure, in a template that is well understood by your model and your algorithm, you're going to apply your algorithm on that structured data, and then you're going to make conclusion, visualize it, and prepare the policy and knowledge at the end of the table, end of the pipeline. So keep in mind, we are at the early stage of the data pre-processing, and I'm going to talk about data integration. We have spoken of noise. We have spoken of basically DBSCAN and clustering a little while back, and we are in the data integration. Data integration means you may have different sources of data coming in. For example, if you have a metadata, you could have name, you could have meaning, you could have data type, you have range of values. You could potentially have even null roles. If you're doing a database design, you could potentially allow the user and the client to basically have some empty cells. And this is a variety of types of data is coming at you. And what you want to do, you want to basically take a look at all of these data that is coming in and make it a structured data for your algorithm, for your model to basically analyze that. It's kind of a mapping from an existing pool of data. You want to map it into a template, and that template is the only template that is going to be understood by your algorithm, your model. An attribute may be redundant if it can be derived from another attribute or set of attributes. Let me give you an example. For example, if I tell you what my date of birth is, can you tell me how old I am? Yes, you can. By subtracting today's date and the date of my birth, you can tell me not only the number of years, but also number of months and days of my age. But if I wanted to simplify this a little bit more, if I tell you what my age is, can you tell me which year I was born? Not the month, not the day, just the year. You are going to take the year we are in, minus my age, and then you're going to tell me which year I was born. So these are repetitive, these are redundant. You don't really need to have redundant information, redundant piece of data in process. It's going to cause a bit of a challenge with your processing. Because if you have redundant, the algorithm, the model is going to say, okay, what is it supposed to be? Is this supposed to be a differentiating attribute? Is this differentiating or is it the same? So if you wanted to take a look at the face, you want to have differentiating components of the face. If everything is the same, then the face is not well recognized. That's why the model needs to deal with the attributes that are distinctive. We don't want redundancy to be there. One of the things that we could do correlation analysis. We can see if we can find the redundancy. For example, if two things are related together, such as my age and the date of birth, I could potentially correlate that. And I can see that these two columns are heavily correlated. We're going to talk about correlation in a moment. We could also use chi-square. It is written as chi, but it's pronounced as chi. Chi-squared, and this is going to be x to the power of 2, noted as such. I leave you with this slide to go deep inside. This is kind of a math-related slide. I let you to dive into that. I'm going to go and talk about the practicalities. In terms of calculating the chi-square, I need the observed data, and I need the expected data. I'm going to show you how to calculate that in a moment. And then we have degrees of freedom. Degrees of freedom, if you have R number of rows, if you have C number of columns, C coming from the first letter of column, R minus 1 times C minus 1 is going to be your degrees of freedom. We have spoken of degree of freedom, and the reason we needed to subtract 1 from R and 1 from C. In the early recordings that are available on YouTube, you can go back if you wanted to and refresh your memory as to why we are going to subtract 1 from the number of rows from the number of columns to get the degrees of freedom. I want to give you an example, and in order for me to give you an example, I want to talk to you about this informative website, mathisfun.com, and that's interesting. So take a look at this picture. You take a look at this one. This is kind of a boating or boat racing. The question is, what type of people would choose boat racing? You would like to take a look at this. You could say single people. 47 of single people have been choosing boat racing. 71%, 71 people who were married and 35 who were divorced. And you want to see yes or no in terms of boat racing. Take a look at the opera or a concert. We have collected 44 singles, 85 married, and 40 divorced. And we want to know the preference of the people, whether you're being married or you're being single or you're being divorced, has any impact in your selection of enjoying a concert or not. Let's take a look at one example. Which holiday do you prefer? We collected we basically provided a questionnaire. We conducted a survey. We came back from those pieces of data that is coming at us, and we understood that 209 men chose beach as their favorite place for holiday, and 280 men have chosen cruise as their favorite holiday. On the other side of the scale, women, 225 women have chosen the beach as their favorite holiday destination, and 248 women have chosen cruise as their destination. You might take a look at this and ask yourself, would the gender affect the preferred holiday? Take a look at this data. If I wanted to just visualize it by human intelligence, I would say there is a huge distance between 209 and 280. There is a huge difference. And I'm going to say men often would prefer cruise over the beach as their favorite destination, holiday destination. But is that so? We are going to investigate that. Now take a look at the women, in terms of gender. You could see 225 and 248. You are going to say, this seems to be quite close. Apparently women have no preference. They could potentially enjoy beach as their holiday destination, as well as cruise as their holiday destinations, with a slight tip of a balance toward the cruise ships versus the beach side. If gender does affect preferred holiday, we say that they are dependent. The gender and destination, holiday destination, are dependent. Remember, when we talk about redundancy, we talk about dependency. We want to understand whether something can be derived from something else, or at least to understand how they are dependent on each other, and factor in the dependency in the model we are going to actually utilize. We are going to do some calculation. We are going to find that the p-value, remember we discussed the p-value a bit back in an earlier stage, and the p-value seems to be basically bigger than 0.05. In this case, it is bigger. We believe that the variable is independent, not linked together. What does it mean? There is no relationship between the gender and the destination, holiday destination, the type of holiday destination we listed here. There is no relationship. Why? We chose P as 0.05 as our destination, and we came to calculate the P from this available table, and that it is more than 0.05, and therefore the gender and the preferred holiday destination are independent. How did we do that? We are going to actually take a look at that in a moment, and we are going to actually calculate that in detail. So I want to ask you to stay with me until you see how the calculation is done. let's take a look at another example. So we have men, 207 of the men have preferred cat as their pet, and 282 have preferred dog as their pet. On the other side, 231 women have preferred cat, 242 have preferred dog. Now, as a human being, if you wanted to take a look at the data and make a conclusion, once again, you are going to say, listen, we have a huge difference between male preferring dog as a pet versus not much of a difference for female choosing either cat or dog as their preferred pet. We go ahead, we calculate the P. We are going to see how this calculation is done. And the calculation is 0.043, and it is less than 0.05. And the result is this is significant, which means the variables are not independent. They are dependent. They are not independent, they are dependent. So what does that mean? Gender and the pet preference have a relationship. They are dependent on each other. So you could potentially choose a different P. Remember, P could be 0.01, P could be 0.5, P could be 0.001. Usually we want this, this P to be very small. 0.05 is good, 0.01 is basically very tight. We spoke of that this is going to be, sounds like high, but with a K, so it is going to be chi-square as we explained, and this is going to be x2. Now, let's take a look at this and the pet preference. How do we calculate the chi-square? Now, we go back to the original table we have. We are going to sum up 207 and 289. That's going to be 489. We are going to sum up 231 and 242. That's going to be 473. When we add 489 and 473, we came up with 962. What does it mean? Although I gave you a snapshot of male versus female, I gave you two different sets. I'm actually giving you a chance to take a look at the bigger set. If you pull them together, the two smaller set together, I'm going to have 96.2 members of the sample. 489 of them is going to be male. 473 of them is going to be female. Let's try this one more time. 207 and 231 is going to give me 438. 282 and 242 is going to give me 524. If I add them up, I have to get to the same conclusion because that's the total sample size. I combine the two samples. So I'm going to have 962. And what does that mean? From this 962, I have 438 who preferred cat. I have 524 who preferred dog. So I had a smaller samples and I had larger the large sample where I actually aggregated all of the data in. Let's just start calculating. How do I calculate the expected value? The way I'm going to calculate the expected value is this: 489, 438 divided by 962. One more time. 489 times 438 divided by 962. 473 times 438 divided by 962. Okay. 489 times 524 divided by 962. 473 divided by, times 524 divided by 962. That's the way we are going to calculate. And if you have calculated these values, you're going to get 222, 215, 266, 257. What are we talking about? We are talking about the large sample. We are talking about 962 sample size. We are not talking about smaller size. If this is your sample, 962, these are your expected values. This is not the same as observed values. Observed values are the little samples, and the little samples could be skewed this way, could be skewed that way, or could be perfectly normal in the middle. Remember the recordings we had early on in the lecture series, in the scientific explorations? This is different. This says if this is your sample size, these are your expected values. 222, 215, 266, 557. There is a big difference between expected value and your observed value. If you take a look at the observed value, 207, 282, quite on the edge on the two sides. But if you take a look at this, you can see that 222 and 267, 215 and 257, you feel that the data is actually getting closer in terms of basically larger size when we take a look at that. Now, you have observed data, you have expected data, you need to say 207 minus 222 to the power of 2 divided by the expected value. So here is my formula. So I think the formula is on the slide. I'm going to actually show it to you here anyway, okay? 207 minus 222 to the power of 2. Again, the minus doesn't, the negative result doesn't matter because you're taking it to the power of 2 divided by the expected value. 282, 266, you subtract them to the power of 2 divided by 266, and that's how you're going to do it. One more time, let's do this and complete this. 231 minus 215 to the power of 2 divided by 215. 242 minus 257 to the power of 2 divided by 257. And we did that calculation and we got the numbers in this table. We are going to add up all of the values. All of the values, when you add them up, it becomes 4.102. This one, this one, this one, and this one. So that's the chi-square I have, 4.102. Now, in terms of degree of freedom, how much is my degree of freedom? The degree of freedom, I think degree of freedom is here. So basically, number of rows minus 1. I have 2 rows minus 1, 2 columns minus 1. The degree of freedom is going to be 1. Now, how do I calculate the P, the significant value that I need, the threshold that I need? I have a number of ways to do it. You can either go into the table or you can do a chi-square calculator. In terms of table, let's take a look at the table. You've got 4.102 with a degree of freedom of 1. How do you read it? This is degree of freedom. So this is 1, 2, 3, 4, 5. This is the degree of freedom. And this is going to be your chi-square that you see. So degree of freedom was 1 and 4.102. So 4.102 is in here, somewhere here. If I just do a kind of a linear interpolation and attach it to the line, 4.102 is going to actually get me to this somewhere between 0.025 and 0.05, and as a matter of fact, it's going to be 0.04283. If you wanted to make it even better, you could potentially go here and actually punch in the 2x2 matrix that you have found. So you are going to, in this case, I want to punch in, and the way I'm going to punch in, I'm going to punch in the, let's see, 2.7 to a 2. So I'm going to say 2.207, 282, 231, 231, and 242, 242. Okay, so I get the same chi-square, 4.10 sum, and the result is 0.04279. So I would say 0.043, and hopefully that's we have 0.04283. So there is a slight calculation error or perhaps this possibly is just a typo when they wanted to put it on the website. So what does that mean? 0.04283 is, we are going to make a conclusion. And the conclusion is, as you see, this is a nice one, rounded already. This is less than my threshold, 0.05. And therefore, I'm going to say that the variables are not independent. They are actually independent, meaning that there is a relationship between gender and its impact on the pet preference. Now, going back to my example, this is another example when you could say male and female and fiction and non-fiction books or movies. You could potentially calculate, these are the observed value, 250, 200, 50, and 1000. These are observed values. When you add them up, 250 and 200, that's going to be your 450. When you add them up vertically, you're going to get 300. When you add them up vertically, 1200. When you add them up horizontally, 1050. The important thing, and that's a simple test you can do, is that if you add up the last column, you get 1500. And if you add up the last row, you must get 1500. So that's one thing. The second thing is to find the expected value. And the way we are going to calculate the expected value is simple. 450 times 300 divided by 1500. 450 times 300 divided by 1500. And that's going to give you 90. And you're going to calculate the same 360 for 840 and 210. You are going to calculate the chi-square, and the way you're going to do the chi-square is simple. You're going to calculate the observed value, expected value, to the power of 2 divided by the expected value. And you're going to sum them up, and you get 507.93. And then you go in and you potentially locate where it is in the table, and you find, for example, the p-value. And in this case, I think we didn't provide the p-value, but the p-value could potentially be above 0.05 or less than 0.05. This is something you define. This is actually a threshold that has been accepted in the scientific community. We don't want to make it too tight. We don't want to make it too open. 0.05 seems to be the 5% we have been speaking of in the scientific exploration. Okay, so that's the chi-square calculation, and I have shown you the way to calculate that. And keep in mind, you could potentially, you could go to the Google and you could potentially type in chi-square calculator and p-value, and there are lots of chi-square calculators that you could potentially grab and use. Okay. The next thing, and the last one in this part that I would like to talk to you about, is about the correlation coefficient for numeric data. Remember when we said that there is a correlation, that there is a kind of a redundancy, you could potentially identify that using correlation. It could be that it is not redundant, but the correlation is going to allow your model to take into account the similarities that could be found. This is a general equation on correlation coefficient. I'm going to show you the correlation on a different website, but this is, as you remember, the cosine similarities that we spoke of earlier in this session. You could, or the previous session, session 5, where we spoke of text to vector or a slide, we said that there is a cosine similarity. This is coming from that area, and we are going to understand correlation as 1, -1, or somewhere in between. So let me get you to the correlation website. Once again, Math is Fun is a wonderful place for me to actually discuss the correlation, and here is my case. If the data is the X going up and the Y going up, and they are an exact match, they are going to fall on a line, exact line. Remember that linear regression, if all of the data points are exactly on the line, what does that mean? it means that the correlation is 1. It is perfect positive correlation. Similarly, if they go on a line and the line has a negative slope, it's going to be perfect negative correlation. Remember, your data is not going to fit exactly on the line linear regression that we spoke of, and it could be wide, it could be tight. So in this case, if it is tight, you will see that the data are actually quite close to my line, the regression line. And if it is 0.9, still it is a representative of positive correlation. It's not going to be perfect, but it seems to be indicative of a correlation, positive correlation. Similarly, indicative of a negative, a strong negative correlation. Then you get to the stage where the data points are actually wider and spread across the two sides of the line. Your correlation is going to actually decrease. Low positive correlation, low negative correlation, you can see that. And if you take a look at this and you want to have a linear regression done, how do you want to do it? Is it going to be this way? Is it going to be this way? Is it going to be vertical? Is it going to be horizontal? You are going to end up having a puzzle to solve. This is no correlation. If the correlation value is going to be 0, then it means there is no correlation at all. Your model needs to know that, because if it is a strong correlation or even perfect correlation, whether positive or negative, it's going to be an important factor for your model to basically analyze. Temperature versus ice cream sales. You could potentially see that the temperature has gone up and then came down. Ice cream sales have gone up and then came down. And when you take a look at that, that's your temperature versus the sales in terms of dollar sign. In fact, the correlation is 0.9575, meaning that as the temperature goes up, your sale on ice cream is going to go up. There seems to be a relationship. Remember, we as human could potentially say, yes, there is a relationship between ice cream and temperature. Because obviously, if the temperature is high and it is hot outside, I would go and buy an ice cream. But that's you as a human intelligent, and the intelligence that is in you making that kind of observation. That's not the case for computer. You need to actually let the computer make that conclusion using the codes you are going to impede. Sometime this may not be necessarily a strong correlation, and it could potentially be deceiving. So for example, this could be the temperature has gone up. I have actually raised up the temperature and went down on the temperature. The sales have gone up. If you tell me about the linear regression, I don't know what to do. The best linear regression potentially would be here in the middle. Some of them underneath, some of them on top, and the line is going to be here. And the coefficient and the slope of that line is going to be 0. So you're scratching your head and you say, is there a correlation or not? If you take a look at linear correlation, of course, the correlation is 0 and there is no correlation. But of course, if you go about the nonlinear correlation, you can potentially find that there is a correlation between the temperature and the sales. There is obviously, as a human, when you take a look at this image, that's how it's going to look like to you. Correlation does not mean causation. So one thing might cause the other might cause the first to happen. They may be linked by a different thing. You never know. And you need to actually investigate that. So take a look at the correlation between sunglasses and ice cream. When you have high temperature outside, often you actually want to have sunglasses to protect your eyes. When the temperature is hot outside, you want to buy ice cream to cool yourself down. But is that correct to say that there is a correlation between sunglasses and ice cream? Not necessarily. This is an important observation that you need to keep in mind. How do we calculate the correlation? The correlation formula, basically the coefficient, this is a very specific correlation coefficient. It is quite similar to what we discussed early on, especially in the cosine similarity slide. This is going to be x bar, x hat is the average, y hat is the average. You find the difference of the data points and x bar and y bar. You multiply them per data point. You sum them up for the entire sample size. And then you do this separately for xi, x bar to the power of 2, yi, y bar to the power of 2. And then you take the square root because you want to have the size of the vector. Remember that? That's your cosine factor, cosine theta. This is your cosine theta. Now, how do we calculate that? It's easy using Excel file, whatever means available to you. In hand, you can even calculate. This is temperature, this is sales. The first thing you do, you calculate the average. You take a look at the average of this column. You take a look at the average of this column. The second thing you do is that you subtract the average from all of the points on the temperature column. And that's going to be minus 4.5 until minus 1.5. So if you do 17.2 minus 18.7, you get minus 1.5. The second thing is that you do the sales, you take the average and you subtract the average from all of the points in the sales. You get the B column. The B column is going to be 215 minus 402, and that's going to be the value you see. After you calculate A and B, you need to calculate the multiplication of these two. So you're going to calculate this multiplication, and that's what this one is. And if you add them up, if you add this column, you got the numerator. You got the numerator. This is the numerator. Now, A2 and B2, you're going to take every member of A to the power of 2. They become positive. Every member of B to the power of 2, they become positive. And then you're going to sum them up. Sum up the A2, sum up the B2, and then you're going to multiply this underneath, and you're going to take the square root, 0.9575. Temperature, sales of ice cream. And therefore, you're going to declare that there is a strong, very strong correlation between the temperature and the sales of ice creams. The formula that you see on the slide is the same, except that the N has been extracted out. So instead of saying a bar, if you add up the column and divide it by the sample size, and then you take the N out, you're going to actually see that this equation and this equation are all the same. These two equations are the same. There is no difference. You can choose either of them. In this one, still you need to calculate the A bar, A hat, and B hat. So you need to calculate that anyway. In this one, obviously, this calculation, this formula is more friendly, I would say, and it clicks on my cosine similarity function we spoke of the last time, and therefore my correlation analysis is complete. Now, I'm going to go and talk about the other parts of the this slide in the follow-up recording. Thank you very much, and see you in a matter of time. Thank you.